Hi, this is Justin Crooks, AI7SG, and today I'd like to do something a little bit different and just show you some of my favorite RF circuits. Number 5 on my list is the quadrature coupler. In designing RF circuits, you'd be surprised how often you need a 90-degree phase split in a circuit when you're thinking about quadrature mixers or, quadrature modulators, demodulators, or any sort of image reject circuit. This can just be super handy. There's lots of online calculators. I use this one quite a bit. But the idea being, actually, you know what? This circuit's wrong. Let's fix it. Okay, so now we've fixed the circuit. You actually do have to terminate the unused leg. Sorry about that. So essentially, you have your input waveform. It's going to go through this quadrature splitter, and you end up with two 90-degree out of phase outputs. Number 4 on the list is just a kind of a funny application of the quadrature hybrid. This is the crossover circuit. What's interesting about it is it's a perfectly planar design, you can see, but signals injected at the top here actually come out the bottom, and signals injected at the bottom actually come out the top. You can see I shifted the frequency and the amplitude so you can see the difference between the two waveforms. But yeah, it goes from top to bottom and then bottom to top. Number 3 on my list is the Wilkinson divider or combiner. That is not what's shown here. This is the absolute simplest way to split a frequency in a semi-lossless fashion. Basically, what I've constructed is two 50 ohm to 100 ohm impedance transforms. So here, if we take this 50 ohm, let's just call this the source, and transform it to 100 ohms and do the same over here, 200 ohms in parallel is going to be 50 ohms, which will match nicely. The problem with this, it works great when both the loads are 50 ohms, but let's say there's some SWR on one of the sides. What you're going to see is a very uneven combining. Here, 2.5 dB different, and we're only at a 2-to-1 SWR. The Wilkinson divider or combiner is typically composed of 70.7 ohm segments and this 100 ohm resistor, which acts as a termination. And what happens now is, here we have basically a perfect split, but even if this arm is almost completely shorted, we still get that same 3 dB output on this arm. And if this were perfectly open or close to it, same thing, this arm stays right around 3 dB insertion loss, which is a perfect lossless split. Number 2 on my list is an RF equalizer. A lot of times you'll have an amplifier that has a negative gain slope, so the gain at high frequency is, maybe 3 or 4 dB lower than the gain at low frequency. In addition, there might be some higher frequency losses in your circuit, so you want to equalize all that out. So at the end of your amplifier, you have kind of a flat gain response. This equalizer circuit starts with just like a fixed T attenuator, and then it adds a high frequency bypass cap, and then also choke essentially for the high frequencies so that all of the energy at the higher frequencies goes around the attenuator. You can start with a basic T attenuator calculator. There's a whole bunch online. And what's nice about this circuit is if you look at the SWR here, we can see it is essentially reflectionless. So in spite of applying this 6 dB attenuation at low frequencies, because of the architecture, it's virtually reflectionless. Coming in at number 1 is the resistive directional bridge. Analog Devices has a great write-up on this circuit if you want to Google it. I have built a little simulation here. The idea is energy going left to right is exactly going to cancel across the reverse positive and negative differential voltage, and energy going right to left is exactly going to cancel at this forward differential voltage measurement. You can use these differential measurements. Here I've computed them just as an actual independent voltage to do things like measure the return loss or even the SWR like I've done here. Here's the equation for SWR, and here's a plot of this simple little low-pass filter, SWR versus frequency.